Think of a function as a little machine. You drop a number in one end, and it hands you exactly one number back out the other. The number going in is the input, x. The number coming out is the output, f of x. Feed in 2, and out comes f of 2. One firm rule makes it a function. Every input gets exactly one output. Same number in, always the same number out. Never two. Now, how do we picture the machine? We give it a home, a grid. The floor measures the input x. The wall measures the output f of x. Take one input, climb up until you reach its output, and drop a point right there. That single point records. This x gave this f of x. Now sweep the input across the whole floor and watch the point ride up and down. The trail it leaves. Every input paired with its output is the graph of the function. So a graph is nothing mysterious. It is just the whole collection of points, x and f of x, drawn at once. Read the shape, and you read the function. Every function comes with two questions. Which inputs are allowed, and which outputs actually appear? Those are its domain and its range, and you can see them both as shadows of the curve. For the domain, shine a light from above and let the curve cast a shadow onto the floor. Everywhere the shadow lands is a legal input. Here the shadow fills the whole floor. The domain is every real number. For the range, cast the shadow sideways onto the wall instead. The curve never dips below 0, so the shadow starts at 0 and climbs. The range is 0 and everything above it. Domain along the floor, range up the wall. Get into the habit of finding both the moment you meet a function. A handful of curves show up again and again, and knowing their shapes on sight is half the battle. Let's tour them, one clean picture at a time. First, the straight line, y equals x. Slope 1. Marching up through the origin. Domain and range are both every real number. Bend it, and you get the parabola. Y equals x squared. A U-shaped ball resting on the origin. It never goes negative, so its range starts at 0. Raise the power once more, and it turns into an S. The cubic, y equals x cubed, dives down on the left and shoots up on the right, passing through the origin. Now something with a hole in it, 1 over x. Two separate branches that race toward the axis but never touch them. The axes are asymptotes, and x can never be 0, because dividing by 0 is forbidden. The square root of x lives on only half the floor. You can't take the root of a negative, so the domain is 0 and up. The curve simply doesn't exist to the left. Last of the basic 6, the absolute value. It folds the negative side straight up, making a sharp V. Smooth everywhere, except that corner at the origin. Remember that corner? It comes back to bite people. Two more deserve a spotlight because they run all through calculus, and they are secretly the same picture. Meet e to the x and the natural log. E to the x is always positive. It hugs the floor on the left, sails through the point 0, 1, then rockets upward. Its output is strictly greater than 0 forever. Now flip that curve across the diagonal line y equals x, like folding paper along it. Watch what the reflection becomes. The reflection is the natural log. It is the mirror image of e to the x, which is exactly what it means to be the inverse. Point 0, 1 becomes 1, 0. So domain and range simply swap. E to the x takes every input to a positive output. The log takes only positive inputs, back to every output. Mirror twins. Here's the real payoff. Once you know a base shape, you can shove it around the grid without ever replotting from scratch. Start with our parabola. F of x equals x squared. Add 2 to the whole thing, f of x plus 2, and the entire curve lifts straight up by 2. Adding on the outside moves it vertically. Now the sneaky one, f of x minus 2. You'd guess it slides left, but it slides right by 2. Subtracting inside, next to the x, always moves the graph the opposite way you expect. Multiply the output by 2 times f of x, and the curve stretches vertically. Every height doubles, so it grows steeper and narrower. Put a minus sign out front, minus f of x, and every output flips sign. The whole ball reflects across the floor and opens downward. 4 moves, and you can bend any base shape to your will. Add outside to shift up. Subtract inside to shift right. Multiply outside to stretch. Negate to flip. That's the whole toolkit. Some curves have a built-in symmetry, and spotting it saves real work. There are 2 kinds. On the left, even. On the right, odd. An even function satisfies f of minus x equals f of x. Draw only the right half, then reflect it across the vertical axis, and it lands perfectly on the left half, like x squared or cosine. A mirror. An odd function satisfies f of minus x equals minus f of x. Take the right half and rotate it a half turn about the origin, 180 degrees, and it becomes the left half, like x cubed or sine. A spin, not a mirror. Mirror on the left, half turn on the right. Most functions are neither. But when one is even or odd, half the graph tells you the other half for free. To last ideas. First, composition. Plumbing one machine into the next. Feed x into G, catch what falls out, and pour that straight into F. What comes out the far end is f of g of x, the composition. But be careful. G must accept x, and its output must be something f can accept. The domains have to line up. Second, the inverse, the machine that undoes f. Geometrically, it is dead simple. Reflect the graph across the line y equals x, and you have it. Fold the picture along that diagonal, and f becomes its inverse, f to the minus 1. Every point A, B turns into B, A, input and output trade places. That's all an inverse is? Let's put it to work on a classic. Find the domain of f of x equals the log of x minus 2. In other words, which inputs are even allowed. The log only accepts positive inputs. Feed it 0 or a negative and it breaks. So whatever sits inside must be greater than 0. Here that inside is x minus 2. Solve x minus 2 greater than 0 and you get x greater than 2. So the domain is every number strictly above 2, written to infinity, open at 2, because at exactly to the log would blow up. To quick companions, the range of sine, the wave rises to 1 and sinks to minus 1, and it lives forever between those two rails. So its range is minus 1 to 1 and nothing outside, an absolute value. The v is perfectly continuous. But at the tip, the slope jumps from minus 1 to plus 1. Because those two slopes disagree, the derivative simply doesn't exist at x equals 0. That is the textbook corner. Your turn. Starting from the plane parabola, f of x equals x squared, sketch f of x minus 2 plus 1. Pause the video and work out where the bottom of the ball ends up. I'll wait. Here's the walkthrough. The baseball sits with its vertex at the origin, 0, 0. The x minus 2 shifts it right by 2. Remember, inside the function moves it the opposite way. So minus 2 goes right. The vertex slides to 2, 0. Then plus 1 on the outside lifts the whole thing up by 1. The vertex settles at 2, 1. So the answer is x minus 2, all squared plus 1. The same ball moved right 2 and up 1. If you landed there, you've got it. Trap 1. Forgetting where a function is even allowed to live. Square roots need a non-negative inside. 1 over x forbids 0, and logs demand a strictly positive input. Always check the domain before anything else. Trap 2. The one everybody trips on. F of x minus 2 moves the graph right, not left. Anything happening inside the function? next to the x, acts in the opposite direction from what your eyes expect. Trap 3. A times f of x is not the same as f of a times x. Multiplying on the outside stretches the graph vertically. Multiplying inside squeezes it horizontally. To completely different moves. Let's gather it all up. A function is a machine. Each input goes to exactly one output, f of x. The domain is the inputs it accepts. The range is the outputs it produces. Find both. Every time, carry a mental gallery of the standard shapes: line, parabola, cubic, 1 over x, root, absolute value, the exponential and its mirror the log, and the trig waves. And know the four transforms cold. Add outside to shift up, subtract inside to shift right, multiply to stretch, negate to flip. Finally, watch for symmetry. Even folds across the y-axis, odd spins about the origin. Master these, and you'll read any function's picture before you compute a single thing.